Welcome everyone to yet another exciting episode of the Thoughtworks Technology Podcast. I'm Prem. I'm one of the regular hosts on the podcast, and today I've got with me two of our almost regular guests now, Neal Ford and Mark Richards. Do you folks want to quickly introduce yourselves again, please?
Sure, I'll go first. I'm one of the regular hosts as well, but I'm also a frequent guest, and that's the role I'm playing today. And Prim's putting a lot of pressure on us, claiming up front that it's going to be an exciting podcast. So we'll see if we can deliver on that. And I'm joined, as I often am on the podcast, with my co-author and frequent collaborator, Mark Richards.
Well, hello, everyone. My name is Mark Richards, and I am, in fact, seems like now a frequent guest on the Thoughtworks podcast. Thank you so much again for having me on yet another podcast.
Excellent. So, what are we talking about today? So, you folks are writing yet another book, and this time it's the second edition of your software architecture fundamentals book. So, what's the motivation for you folks to write the second edition?
Well, in fact, it's already published. We did finish that up at the beginning of the year, and it was released in, I believe it was April. Neal, is that correct?
That's correct. Just a couple of months ago as we record this.
Software architecture does remain more stable, I will say, than, at least as a field, than other areas of technology. However, that said, it does change. And Neal and I were reviewing our book, The Fundamentals of Software Architecture, the first edition, that we published in February of 2020, and realized there actually were some things that changed in software architecture that we did not include in the book, and felt like it needed an update because of that.
Well, and part of that came in the interim. We collaborated with Rajiv Gandhi and wrote Headfirst Software Architecture. And as we were revisiting the subject again, we realized that there were some deficiencies in the original source material because the Headfirst book covers about a third of what the Fundamentals book covered. But it also covers some things the Fundamentals book didn't cover, like one of the things, to Mark's point, that has become notably more popular in the intervening time are modular monoliths as an architecture style. And so we only passingly mentioned those in the first edition, but they got a proper full treatment for their own chapter in the second edition, just like they did in the Headfirst Software Architecture book. So that's just one of the many changes that we were reacting to in the ecosystem.
Well, and one of the other aspects that we didn't touch on a lot in the first edition was the aspect of data within software architecture. And so we did add quite a bit, especially within the part 2 of the book, where we talk about the architectural styles. We did add a full sections on data implications and data topologies within each of those architectural styles we discussed in the book.
Well, I think in the first edition, it wasn't so much that we didn't talk about data. We just didn't talk about it consistently. Some of the styles we talked about data, like microservices. Data figured heavily in service-based architectures, but then we hardly mentioned it in layered architecture. And we realized, and that's one of the other things we wanted to fix. So one of the things that when you write a book like that, one of the great things about writing a book is when it's done, it's finally done, which is a great relief, particularly for this particular book, which is quite the effort to get done. But then it's very static. And when you see things in it that you don't like, it's hard to fix because it's done. And so it's very frustrating when you're used to software, because software is very soft and books are very, very hard compared to software. I mean, you can change the electronic version, but it's much more difficult to change the entire chunk of IP. And so over time, we became frustrated. So one big part of our book is the second section, which is a catalog of all the architecture styles. And for all of those styles, we have a bunch of pros about how they're different, and we compare them with some charts, et cetera. But the sections in all those styles weren't consistent because we were just talking about the highlighting features of those styles. But then we realized, well, that leaves a gap for questions. Well, how does this style handle the highlight from this other style? And so we made the styles much more like a catalog where every styles chapter is rigidly consistent in terms of the sections that it covers, and it covers every aspect of every one of the styles. A great example of that, of one of the ecosystem changes, was we didn't have quite the nomenclature to understand the impact of team structure on architecture until team topologies came out. And that gave us a great lens to think about that intersection. And so every style now has a section that talks about how well does this align with some of the ideas in team topologies as a way of distinguishing those architecture styles.
And also, we didn't really touch on the first edition about some of the common risks associated with each of the architecture styles. We did do the quantitative analysis in terms of the star ratings of what it's good at, what it's not good at, but there were other orthogonal risks associated with some of these architectural styles, which we did add in the second edition, along with some governance techniques. How do we govern some of the aspects of these architectural styles? And also, what are some of the cloud considerations with these architectural styles and when to use them in cloud and when not to? And so those were some of the additional things we added in part 2 of the book.
One of the things that you mentioned are the new fallacies of distributed computing. So what are some that stand out for you, and can you tell our listeners why they matter today more than ever?
When we thought about this podcast, we did not want to just make it a what's new in our second edition, because, if you're not interested in buying a second edition of our book, then it's not a very interesting podcast episode. So we thought we'd talk about some of the things that we added to the book that may be useful as a standalone. And one of those was something that we've gradually, since the book came out in 2020, we've gradually sort of been building on over the last few years and finally wrote down in the second edition. And that's what we're calling the new fallacies. So I'll give the background and then let Mark talk about the new ones. What we're riffing on here is back in the 1980s, I think, Peter Deutsch and some other folks at Sun Microsystems put together a very famous list of the 8 fallacies of distributed computing, which has its own Wikipedia page now. It's all these silly assumptions you make when you move from monolithic to distributed architectures, like bandwidth is infinite and latency is 0 and the network is homogeneous. So it's all these. I tell people that are new to distributed architectures, you should really study that list that Peter Deutsch created, because you'll learn them one way or the other. You'll either learn them by reading the list, or you'll painfully learn them one at a time as part of your professional career. I think reading the list is an easier way to learn them, but you can do whichever you prefer to do. And so that's the background. But then Mark and I have talked about these so long, and we've also talked about distributed architectures like microservices so long, that we realize that we've identified some new ones. And so we've sort of, a little tongue-in-cheek, started adding to the 8, and we've come up with 3 more that we finally documented in the second edition of our book. We've been talking about these live for quite a while and figured it was finally time to document them. So I'll let Mark start talking about the new fallacies that we've come up with.
These fallacies really were born out of what Neal was talking about in terms of lessons learned and experiences, just like the original 8 were. And our first new one, fallacy number 9, is versioning is easy. Just version it. And well, it might seem like it's easy just to simply version a shared library or version an API or a service. But there's a lot of complexity that both Neal and I have experienced with versioning any sort of software or artifact. And one of those first complexities is when you make a version change, how do you communicate that version change to all the users of either your software or that particular software artifact? How many versions should you maintain of a particular artifact? If I have a shared library, a jar file or a DLL or a gem, should I keep out 3 versions, 4, 10? What about an API that maybe the public is using? And then the third complexity we identified was, if I want to deprecate a version, what is my deprecation strategy? How do I communicate that deprecation to the many teams and users using that particular artifact or API? And also, what if I need to deprecate a version due to a breaking change, something that's no longer supported, and I have a team using that particular artifact that says, well, we're in a 3-month code freeze. We can't change. These are the inherent complexities involved with versioning, and not just simply determining the versioning numbers or whatever the dot notations are.
It's also the scope of deprecation. Is it per service? Is it per domain? Is it per API? Is it per system? So it's one of those things that's like, it's an easy solution. Oh, we'll just version it. And then suddenly you realize that you've fallen into a tar pit.
Definitely, versioning is not easy.
Exactly.
So that's number one. What are the other two?
So the second one I'll talk about. So every time you see a presentation about microservices and they're talking about transactional workflows in microservices, traditionally known or colloquially known as sagas, they talk about the role of, okay, so what if you can't rely on a database to do a consistency for you? You have to implement eventual consistency. And one of the patterns that you use to do that is have some mechanism, either an orchestrator or one of your domain services, after you've found an error, issue a compensating update to fix up the ones that you've already fixed. And so you can bring back a consistent view of the world. So if there are 3 services involved in a transaction, you're able to update the first 2, but you can't do the third one. The role of the orchestrator in that case would be to go to the first 2 and tell them, roll back your changes so that the whole world looks consistent from a workflow standpoint. That's known as a compensating update in the microservices world. So that brings us to our second fallacy, which is that compensating updates always work. Because when you see somebody do a presentation of microservices, at some point they wave a magic wand and then say, oh, well, then a compensating update occurs and then everything is back the way it was before. But then they never talk about, well, what if the compensating update fails? And so there are really 2 different error scenarios that bring up a lot of interesting side effects and boundary conditions, et cetera, that you have to take into account when you build systems like that. So we don't like those sort of magic wand that sweep complex things under a rug, and that's definitely one of them. But that's the number 10, which is compensating updates always work, because they don't, and when they don't, it can get really messy.
And then we have a third new fallacy, fallacy number 11, which is in distributed architectures, observability is optional. And this was born out of frustration of both of us experiencing the fact that observability is not treated as a first-class citizen in a lot of the systems we work on. And in fact, it's a kind of a last-minute thought or a bolt-on after all the functionality is done. And in fact, this fallacy points to the fact that observability is not optional, and it should be treated as a first-class citizen to be able to analyze both the operational aspects of a particular system as well as the non-operational or process aspects of that system. And without observability, we have no insights into whether we are scaling, but tomorrow we won't be. And those are just examples of some of the operational aspects. But this fallacy, we both feel, is very key and important for those working, especially in distributed architectures, to really understand what data we need. Where do I get that data? And how to validate all of the capabilities of that architecture, both operational and non-operational.
The other thing that we added to the second edition of the book was we updated, really just added to, didn't change, the laws of software architecture, which were a little bit tongue-in-cheek in the first edition. So when we were writing the first edition of the book, we were quite ambitious, and we thought, we're going to, as we go through all this material, we're going to see if we can identify things that seem universally true throughout software architecture, and we'll call those the laws of software architecture. And we were hoping to find like 10 of them, and we found 2 in the first edition. And the first of which was that everything in software architecture is a trade-off, which we still stand by, and that has survived quite nicely. There was a corollary in our first edition that if you think you found something that isn't a trade-off, you likely just haven't identified what that trade-off is yet. In this second edition, we actually added a second corollary to the trade-off law, which is you can't just do the trade-off analysis once. And for complex problems in software architecture, it's always about trade-offs. And it would be nice if you could just go into an organization and take a complex problem and just think really, really hard about it for like 2 or 3 days and do the trade-off analysis, one big time, and then be done with it forever. And that's what we're going to do for the rest of time. The problem with a lot of the software architecture decisions, though, is that there are a lot of variables involved, and those variables are always slightly shifting and changing. So one of the examples we give in our book is, shared library or shared service. You can come up with this whole list of pros and cons, but then every time you make that evaluation, some of those are going to change. How many platforms you're supporting, what kind of volatility can you support, et cetera. And so really complex questions in software architecture, it would be nice if we could make one decision about orchestration versus choreography, or mediation versus brokering, or shared libraries versus services. But every time we encounter those situations, there are enough differences present in our ecosystem that we have to respond to them differently every time.
Another thing which is very important that you cover in this book is this aspect of measuring and governing architecture characteristics. Can you shed some light on what you mean by that? Why it matters? How you can do it?
We can probably fill up 7 Thoughtworks podcasts with this topic. It kind of follows on that 11th point we talked about with that fallacy of observability is optional. This is one of the reasons why we created that fallacy, because it's not optional, and then it leads to the measuring and governing of architecture characteristics. It's interesting. We talk about mostly governing operational characteristics of an architecture. Things like scalability, responsiveness, fault tolerance, availability. Those are 4 key ones. That we do have a lot of observability tools and platforms that tend to measure those aspects. However, in the second edition of the book, we kind of really took a step beyond just the simplicity of those kind of measurements of architecture characteristics, and looked at other aspects of an architecture or architectural style that we govern and measure as well. And let me give you a great example, and then I'll let Neal give some examples. Let's talk about event-driven architecture. Event-driven architecture we may choose for its high levels of scalability and fault tolerance and responsiveness, as I mentioned before. But there's other aspects we added to the book in terms of governing these kind of architectures. For example, with event-driven architecture, we rely on asynchronous processing with highly decoupled services that trigger events and then respond to those events. One of the things we can actually measure and govern is the amount of static coupling that we have within services in an event-driven architecture. And that static coupling can be in the form of event payloads, the rate of change of an event payload. When we change the payload of an event that's being triggered, it may be responded to by dozens of services. And when I implement that change, I can potentially break all 12 of those services, making my highly decoupled event-driven architecture quite brittle. And this is one out of many examples where we start talking about the structural aspect in terms of the governance. For example, in mine here, coupling as a good example of something that we tend to forget about when we start focusing on operational characteristics. And these things are just as important as those typical operational ones from a measurement and governance standpoint.
Yeah, that's another thing that we made more consistent in this book. We had in the first edition a chapter about governance, and we still have a chapter about governance here talking about automating with architectural fitness functions using tools like ArcUnit or NetArcTest or tools like that. But then for each one of the styles, we also talked about the particular challenges of governing those styles. Mark mentioned some of the challenges in event-driven architectures. We mentioned some of the challenges in modular monoliths and layered architecture. So that's another thing we want to make more consistent, because Well, Mark and I are on a bit of a crusade here to try to reclaim the governance word in software architecture because it has such a bad reputation. Because for so long it meant, mindless bureaucratic things that don't seem to add any value, but just a punch list of things that are annoying. And it doesn't have to be that. The real idea behind it is not only do you define these important capabilities of your architecture, but you should be able to govern them, to measure them, to see are they still true, and to test them. That's the essence of agility in architecture is fast feedback. I did a change we just made. Did it break something? And how quickly can I find that out? That's really the aspect of governance that we're trying to attack here. And trying to shine a light on each of these styles because all these styles, these generic styles, they all have pros and cons associated with them. So given that we've made an intelligent choice, there are still negative aspects of this that we have to mitigate. So how can we do that via governance?
I want to also provide another good example because, Neal, you mentioned an entire chapter that we added to the book on the modular monolith, which has become quite popular as a choice of a monolithic style, either as a stepping stone for distributed architectures in the future or even near future, or as a final resting place. But when we start talking about governance and those kind of things within a monolith, that structural aspect can, the importance of it is the success of that architectural style working. For example, a modular monolith is broken apart or partitioned by domain, or specifically within this architectural style, a module. And what we do is we delineate our functionality by domain or subdomain represented as a module. There's three kinds of governance and measurements that we can take on a modular monolith to ensure its success outside of all the characteristics that we've identified. For example, does all the source code inside our modular monolith adhere to the specific modules we identified and those corresponding domains? That's one. Another way we can govern is the amount of communication between those modules. This is such an important measurement and governance because we want those modules to try to remain as independent as possible. And we do get times where they do communicate. But if our modules, the way we delineate this modular monolith, are all communicating too much, what that usually means is we have not delineated our domains properly or not partitioned our architecture properly based on those types of modules and what they represent. And so these are just forms. A third might be even the independence of each of the modules. How much do they need to communicate? And so these are all structural related governance and measurements that provide yet another example of what we added kind of to the book to really help architects understand these architectural styles, but also appreciate the need for measurements and governance within every one of these architecture styles.
One more thing that was pretty intriguing, which you talk about, which is usually not discussed that often, is the scope of architectural characteristics. You talk about this thing called the architecture quanta, which was, I think, originally introduced in the Building Evolutionary Architectures book, but I think you dedicate an entire chapter to this. Can you talk about what you mean by that, and again why it matters?
That started in the Building Evolutionary Architectures book because Rebecca Parsons, Pat Qua, and I, part of the, so that book is primarily about this idea of architectural fitness functions, which we call the mechanics of building evolutionary architectures. But we also wanted to address the structural question of, given the sort of generic topology of an architecture, like microkernel versus microservices or layered architecture versus microservices, are some of the structures inherently more evolvable than others? And if they are, why? And that was the original motivation for this quantum idea, which was closely aligned with sort of a bounded context, but in an architectural sense. So it more or less defined a bounded context, but from an architectural standpoint. And that was sufficient for the Evolutionary Architectures book, and it was also quite influential on Zhamak Delhagani on her thinking about the way data mesh works. And so she credits this quantum idea as a way of consolidating her thinking about, the scope and boundaries of things in distributed architectures. But then as time has gone by, we've realized that this is a really useful perspective. And so we've done a lot more fleshing out of this idea. We actually ran across, as we were writing Software Architecture, the Hard Parts, this book called What Every Developer Should Know About Object-Oriented Design by Miller Page Jones, which is a book from 1993. Mostly a book about an object-oriented analysis and design technique that nobody outside the author and a handful of other people ended up using. But he also defined this concept of connaissance. And if the people listening don't know what that is, there's a website called connaissance.io that highlights connaissance. It's really a language that describes coupling. And I won't go into all the details of that.
Good luck spelling it.
Yeah, it's a CNNASCENCE, I think, but you'll be able to Google around and find it. And that's really a language that describes levels of coupling. And I won't go into that. It's a useful exercise. But the other thing he identified that we found quite useful was this distinction that Mark was alluding to of static versus dynamic coupling in a distributed architecture. And we tell people who come to our class that when they come to our class, you came in with one term for coupling, which was just coupling, and you're going to leave with at least two, which is static and dynamic. Static coupling is how things are wired together, the dependencies of things. If I need to bootstrap this service, what dependencies need to be there, broker, a database, et cetera. So those are the static dependencies. And that also helps define a scope for a set of architecture characteristics. And so that's what this quantum idea has really become, is a modern way of assessing the scope for a set of particularly operational architecture characteristics. Because if I have a single database, that's going to determine the level of scalability and responsiveness that I'm going to have in this particular service. And so that defines a scope of those operational architecture characteristics. But then the dynamic side of that also defines what happens in distributed architectures. So let's say I have two services running, A and B, and A is running at 10 times the scale of B. What happens when they start calling one another in a distributed architecture? And if A calls B synchronously, what happens? Well, A's performance drops down, the responsiveness drops down to what B's is because it's blocking and waiting for the response from B. And so that's what we refer to as dynamic entanglement in a software architecture. And in microservices, this is a reality because one of the selling points of microservices is that each service can have its own set of architecture characteristics. Therefore, each service may have a different level of scalability and responsiveness and elasticity. And so that dynamic entanglement is something that you have to analyze. It's easier with asynchronous communication, but that's the impact of synchronous versus asynchronous. And so that's this whole idea. That's why we ended up dedicating an entire chapter to this, because it's a really useful way of analyzing some of the most difficult issues in distributed architectures by separating coupling into static and thinking about dependency separately from what happens once I've resolved my dependencies and these things have to start communicating with each other. Like many complex problems in software, decomposing it into two slightly simpler problems allows you to understand it a little better. So that was the motivation for that entire chapter. That's one of the things that's been confusing people for a long time because it is a kind of an abstract concept. And so one of the things that we really wanted to do in the second edition was to try to flesh that out in as expansive as a way as we could. And it expanded quite a bit, including a few word salad. But, it was an attempt to create as precise a definition as possible. So some of the phrases got kind of long to become more precise. But I think at the end of the day, it makes a lot more sense now. So, but I guess our readers will ultimately let us know about that one way or the other.
Great. So the next topic that I wanted to cover was on architecture styles. You cover a variety of them, but a couple that may not be as popular. For example, you talk about space-based architectures. What exactly is space-based architectures? Because it's not something that is as prevalent as something like microservices or event-driven, right? So can you shed some light on that?
when we set out, well, 7 or 8, 9 years ago, I guess, to write the first edition of the fundamentals of software architecture, we wanted to kind of give a holistic view of software architecture in 3 parts. And of course, we were limited by space. As Neal's very fond of saying, this could have been a 20,000 page book or a 200-page book. And there's a lot of, I would say good architecture books that focus on maybe 1 or 2 of the most popular architecture styles. And what we wanted to do was really expand that breadth of knowledge about different architectures. And one of those that was kind of unique is space-based architecture. This, Neal and I, before microservices came out, used to refer to this architecture as a domain-specific architecture, meaning that it was built to solve one particular problem, and that was of elasticity and high levels of scalability. These kind of systems that how do you support 1 million concurrent users or even 5 million concurrent users? Concert ticketing systems that have these spikes of going from several users to several tens of thousands of users instantaneously within the first couple of seconds. These are extremely hard problems to solve in architecture. And space-based architecture is, in fact, one of the ways of solving these kinds of problems. It's called space-based not because of outer space or because of cloud, but because of a computer science term, a pattern called tuple space, which means multiple parallel processors with shared memory. And the idea of space-based is this. Any system, when we start talking about these kind of levels of scalability and elasticity, will have one single limiting factor. That's the database. The database will always become a problem in highly elastic and highly scalable systems. And what space-based does is it effectively removes the database from the transactional or operational equation. And so everything in space-based, all data is cached in memory. And consequently, if you remove the problem, then you no longer have that constraint. And this is this I just want to say is one architecture I'm really fond of. And I'm fond of it because of this one reason. Because this architectural style solves a particular problem. And it forces us as architects to think about other kinds of problems, other kinds of constraints that we have that are preventing us from maybe it's high availability, maybe it's high agility, maybe it's great testability. We always have constraints as architects. And this architectural style causes us to really think outside the box in terms of, is there a way to remove that constraint? Is there a way we can shape an architecture to overcome a particular constraint we have to solve a problem? And I really like that about space-based architecture. Turns out that it used to be, in the first edition of the Fundamentals book, the longest chapter. As a matter of fact, I had to trim it down from, I believe it was, Neal, 85 pages down to 60, I think, just due to the sheer weight of it. Well, I will have to tell you, it is no longer the largest chapter in our second edition. I'm wondering, Prem, if you could guess, it's in part 2, the architectural styles, which chapter became the longest?
I have not actually measured that way, but let's see. If I had to guess, I don't know. I mean, is it in part 1? Give me a clue. Part 1.
It's in part 2. It's one of the other architectural styles.
Wow. Okay. I guess. Look, maybe modular monoliths, or maybe microservices would be my guess.
Well, two very good guesses. As a matter of fact, I figured you would guess microservices. That is the third longest, but it turns out it's event-driven architecture that all of a sudden became almost a sub-book of itself within the second edition, just because of its increased popularity. Thank you, microservices. And as a matter of fact, Prem, speaking of microservices, I'm glad you said that, because as I mentioned, space based, we always considered this specialty kind of architectural style, but microservices breathed a new life into space based architecture. And its limits talk about solving constraints. Well, how do you take 12 and a half terabytes of data in a database and put it all in memory within services? And the answer is you can't. And this was always a constraint within space-based architecture. Well, let's talk about microservices, single purpose services with much more limited data that it acts on. And if you form this hybrid between microservices and space-based architecture, suddenly it's no longer a specialty domain specific architecture, but now can be applied to a whole host of problems because those services in space-based are in the form of microservices with much less data in memory. And so these are other examples of these wonderful kind of constraints I was talking about.
Yeah, yeah. I mean, look, I can totally believe that event driven is your longest chapter, because yeah, I mean, I personally I believe that if you've got monoliths and synchronous APIs, and then now if you want to get looser coupling, then event driven is probably the way to go. But again, there are constraints with that as well, like everything else. But then I have another question for you guys in terms of the microkernel architecture. What exactly is that? And it's also something that doesn't get a lot of press. So maybe Neal, you can shed some light on that.
Yep, it's a shame because it's one of those architecture styles that once you've identified it, you start seeing it everywhere because it's so common. The basic idea of a microkernel is it has a core and it has plugins to allow you to add new behavior to it or change existing behavior. But it's fantastic as an architectural solution for customizability. And it's also a great illustration of the third law that we added in the second edition. So our first edition had two laws. I mentioned everything's a trade-off. The second law that we did in our first edition was that why is much more important than how, which is also still true. But we added a third law so when we wrote the microkernel chapter in the Head First software architecture book, we realized that not everything that supports plugins is a microkernel, but every microkernel supports plugins. So in other words, a browser is not really a microkernel because it's purely functional without any plugins. But something like a linter tool, well, yeah, it'll parse the code for you, but if you don't build any linting rules to plug into it, then it's useless. Eclipse is a great example of the old school Eclipse. If there are no plugins in it, it could barely open and close text files, and that was all it could do. And so we defined in the Head First book, and this made it over into the fundamentals book, and we were surprised that our editor allowed us to do this. We invented a word, the degree of microkernality, of how much behavior is in the core and how volatile is the core, because that's the real key is it a microkernel or not. And that leads to that third law, which is one of the reasons that software architecture decisions are so difficult is that so few of them are nice, convenient binaries. They almost all live on a spectrum somewhere. So is it a microkernel? Well, it depends because there's a degree of microkernality that you have to assess as to, okay, how much functionality is in the core, how much is, and so that's another reason architects are always so grumpy. It's hard to get in these, really definitive, objective battles about things because everything's a messy a spectrum trade-off.
So what you seem to be saying is that the more stable the microkernel is, the more the degree of microkernality, and is that the point?
It is, and in fact, the less functional it is without plugins, the more of a microkernel it is.
Now that you say it that way, right? I mean, Trino, the distributed SQL engine, pretty much works the same way. I mean, the way that it works is it has a bunch of these connectors which allow it to talk to a bunch of databases like relational or Mongo or HDFS and so on and so forth, right? And without those plugins, it's pretty much useless.
Integration hubs are great examples of microkernels. Continuous integration servers are great examples of plugins. You don't plug anything into it, what is it going to do? It's just going to sit there and wake up every hour, and so it's one of those things. So the BFF pattern, the backend for front end pattern that Sam Newman talks about, that's a microkernel because you're plugging in different user interface agents to handle from the same API. So it's one of those, every time customizability comes up, microkernel is lurking there in the wings. And we talk about it as an architecture style that's quite useful to solve this common problem, which is customizability. I mean, that comes up in a lot of different contexts, whether it's operational customizability like continuous integration or user customizability. We talk about in our book, what if you're something like an insurance company in the United States where you have standard policies, but then every state can have their own fiddly rules about how you apply some of those rules? A microkernel is perfect for that because you build a core insurance engine in the middle, and then every state gets their own plugin to modify what needs to happen uniquely for that state. And because they're all plugins, they're all isolated architecturally from each other, so they don't interfere with one another. So it's a really, really useful architecture style.
I've got one more question before we call it a close. Towards the end of your book, you talk about how architecture is about making teams effective, and this is something that not a lot of architecture books seem to cover. So this is definitely something a lot of us would be very interested in learning more about. So can you touch a little bit on that, please?
I'm assuming you're referring to our architectural intersections chapter, the last chapter, or because we had several last chapters.
This is the chapter 24, which says making teams effective, that one.
This is often an overlooked aspect of software architecture, and one which I have found through my 40 plus years of actually working in this field becomes one of the more important aspects of architecture. It's one of the reasons architecture sometimes doesn't work. And making teams effective was the title we gave for basically collaboration and leading and guiding teams as an architect, and the importance of being able to guide the development team through the implementation of an architecture, regardless if that's greenfield, brownfield, or even continually modifying that architecture to add or remove or update the features. And this is a real key aspect, a full third part, as a matter of fact, of the book in terms of the techniques and soft skills. But I will say one that is unfortunately often overlooked, and Neal and I cannot stress enough that half of being an effective software architect and making architecture work are mastering these soft skills, the people skills of architecture.
Yeah, and in fact, we purposely made the entire third part of the book about those soft skills because, the way you become a software architect is demonstrating good technical skills, and then you often get blindsided by these soft skills, which we always put in air quotes because it's often the most difficult things that people run into. But trying to make a team effective is a great example of supporting a team and being able to figure out how to do that is. It's not an easy thing to do, and it requires some practice and skill.
Oh, and Prem, I just wanted to add specifically in the chapter you're calling out, in the second edition, we do show some tools and techniques for how much involvement should you actually have on a development team. In other words, you can really fully derail an entire team by being too involved and too much kind of, quote, in their face. And the opposite is true as well, where if you're not there when the team needs you, how can you possibly expect them to implement the architecture correctly?
You have this speedometer where you have got control freak architect on one extreme and the armchair architect on the other, where one is like, is someone who wants to exercise more control and involvement, whereas the other one is almost like no control, no involvement. So I guess the message is that you need to be somewhere in the middle to be able to be effective for the teams that you're trying to serve.
Well, it's not necessarily, Prem, to be in the middle somewhere. It's just to really understand, given certain factors, how much involvement should I have? And that's the kind of the tool we introduced there, based on things like team familiarity, team size, the duration of the project, the complexity of the project, and these kind of factors to really gauge that dial. To your point, Prem, may point all the way over to control freak, which means most of my time, most of my day better be with that team or they're not going to succeed. Yeah. And so it's rather than finding it in the middle, it's finding out how much involvement I should have. Hopefully it's in the middle. That would be perfect, because then I can actually lead and manage multiple teams. But too many times it's to an extreme.
And it's also about modulating that. So by the way you couch the question, it sounds like you've seen both of those types of the extremes in the wild. But I think part of the instinct for new architects, which is a lot of what this book is targeted for, is to lean more toward the control freak, because now I have the power suddenly, and now I can control all the decisions, and, now I can finally implement things exactly the way I want. And you have to resist that, but not so much that you become so laissez-faire that, it becomes chaos. And so finding that right level, depending on the team, the context, I think is really important. And thinking about what that level is, I think is the useful exercise.
Absolutely. So thank you very much, both of you, for indulging us yet again today. And I'm hopeful that this is yet another exciting episode, as we have called multiple times. And signing off one more time. Thank you very much. Until next time, see you folks.
Thanks, Prem. Always a pleasure.
Right, thank you.